Hello, I'm Sebastian. Welcome to 9 Trees podcast. Today, I will summarize and review the book. The God Equation, The Quest for a Theory of Everything, is Michio Kaku's wide-angle guide to one of science's most ambitious goals. A single framework that unites all the fundamental forces and explains the universe with one coherent set of principles. Written for general readers, the book traces how physicists moved from early ideas about nature and symmetry to the modern landscape of quantum mechanics, relativity, and the search for unification. Kaku, known for making complex physics approachable, places today's front-running candidates, especially string theory and related approaches, inside a longer historical narrative that includes landmark breakthroughs and stubborn contradictions. Rather than presenting a narrow technical argument, he emphasizes the big questions: why the laws of physics look mathematically elegant, what it would mean to merge gravity with the quantum world, and how experimental clues like cosmology and particle physics might guide the next leap. The result is both a history of ideas and a roadmap of ongoing scientific debate. I will give you key takeaways from this book. Firstly, from ancient wonder to mathematical laws. A central thread in the book is how the search for ultimate order evolved from philosophical speculation into precise mathematical physics. Kaku outlines the long arc from early thinkers who tried to describe nature in terms of harmony and geometry to the scientific revolution, when observation and calculation became inseparable. This progression matters because it frames unification as a recurring motif, gravity and motion in Newtonian mechanics, electricity and magnetism in Maxwell's equations, and the deeper idea that symmetry can dictate what laws are possible. The narrative highlights why equations became more than bookkeeping tools. They turned into compact statements of reality that could predict new phenomena before they were seen. Kaku uses this history to motivate a modern question. If earlier unifications were achieved by finding a broader mathematical structure, then perhaps the final unification will also be a discovery of the right structure rather than a patchwork of fixes. This topic clarifies why physicists keep returning to elegance and symmetry as practical guides, not just aesthetic preferences, when evaluating candidate theories for the universe's deepest rules. Secondly, the two pillars and their tension, relativity versus quantum theory. Kaku devotes major attention to the extraordinary success and deep incompatibility of the 20th century's two foundational theories, Einstein's general relativity and quantum mechanics. Each describes nature with stunning accuracy in its proper domain. Relativity explains gravity as the curvature of spacetime and governs planets, stars, black holes, and the universe at large. Quantum theory describes the probabilistic behavior of particles and fields, powering modern technology and accounting for microscopic interactions. The problem arises when both must be applied at once, such as near singularities, inside black holes, or at the earliest moments after the Big Bang. The mathematics becomes unstable, producing infinities and conceptual contradictions about what spacetime even means at tiny scales. Kaku frames this clash as the main reason a theory of everything is needed. A genuine unification must preserve the tested predictions of both frameworks while revealing a deeper layer in which they are reconciled. This topic explains the stakes. Without a quantum theory of gravity, certain questions in cosmology and high-energy physics remain incomplete, and our understanding of reality stays split between two incompatible descriptions. Thirdly, symmetry as a compass, the Standard Model and beyond. Another key topic is how symmetry principles organize modern particle physics, culminating in the Standard Model. Kaku discusses how forces can be understood through gauge symmetries and how particles emerge as excitations of underlying fields. This framework successfully unifies the electromagnetic and weak nuclear forces and gives a structured account of the strong force, while also describing a zoo of particles in a systematic way. Yet the Standard Model also signals its own limits. It does not incorporate gravity, it leaves open questions about the values of fundamental constants, and it relies on ingredients that do not feel final, such as multiple particle families and parameters that must be measured rather than derived. Kaku uses these successes and gaps to show why unification cannot stop at the Standard Model. He also connects this symmetry-driven approach to the broader dream of a single equation, suggesting that the same logic that made earlier unifications possible might extend further if a more encompassing symmetry exists. This topic helps readers see unification as a method, identify the symmetry, derive the interactions, and test the consequences in experiments and observations. Fourthly, string theory and the promise of quantum gravity. Kaku presents string theory as a leading candidate for bridging quantum mechanics and general relativity. In this view, the fundamental building blocks are not point particles, but tiny vibrating strings, and different vibration patterns correspond to different particles, including a quantum carrier of gravity. One of the book's recurring ideas is that changing the basic premise from points to extended objects can soften the infinities that plague attempts to quantize gravity directly. Kaku also highlights how extra dimensions, supersymmetry, and rich mathematical structures enter naturally, not as arbitrary add-ons, but as consequences of internal consistency. At the same time, he addresses why the program is controversial. The energy scales involved are far beyond current particle accelerators, and the landscape of possible solutions raises questions about uniqueness and testability. This topic is important because it shows what a theory of everything must accomplish in practice: produce known physics as an approximation, explain gravity in quantum terms, and still generate predictions that can be confronted with data. Kaku's treatment frames string theory as both a bold synthesis and a work in progress, whose ultimate status depends on future evidence. Lastly, clues from the cosmos, Big Bang, black holes, and experimental hints, the book connects the hunt for a final theory to observational frontiers where quantum gravity effects might leave traces. Kaku discusses how the early universe provides a natural high-energy laboratory, since conditions near the Big Bang approach the regimes where current theories collide. Cosmic background radiation patterns, the distribution of galaxies, and the behavior of space-time under extreme conditions become potential sources of indirect evidence. Black holes play a special role because they concentrate mass and warp space-time so intensely that quantum effects cannot be ignored, raising puzzles about information, entropy, and the fate of matter. Kaku also points to the broader experimental ecosystem. Particle physics searches for new symmetries, precision measurements that test the standard model's boundaries, gravitational wave astronomy that probes strong field gravity, and astrophysical observations that may constrain new physics. The message is that a theory of everything is not only a mathematical quest, but also an empirical one, shaped by what nature allows us to observe. This topic helps readers understand how progress can occur even when direct access to Planck-scale energies is impossible, by using the universe itself as the experiment and looking for subtle signatures that discriminate among competing ideas. In conclusion, this book is best for curious general readers, students deciding whether to pursue physics, and science fans who want a coherent map of why unification matters and what stands in the way. It also suits readers who enjoyed popular science accounts of relativity or quantum mechanics but want the next layer: how these theories connect, conflict, and motivate the search for quantum gravity. The benefit is perspective. By tying history, core concepts, and modern research into one narrative, the book helps readers think more clearly about scientific progress, what counts as evidence, and why certain mathematical ideas keep reappearing. Even without advanced equations, the reader gains a practical understanding of the main contenders and the open problems that shape current physics. Compared with many similar books that either focus narrowly on one theory or stay at a purely inspirational level, Kaku aims for a balanced survey that explains both the appeal and the criticisms of proposed unifications. That breadth makes it worth buying as a single-volume introduction to the theory of everything conversation, especially for readers who want big ideas anchored to the real constraints of experiment and the history of physics. If you would like to support Michio Kaku, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.